Next, we are going to types of reactions.
Morning, ma'am.
What are the enthalpy changes in different types of reactions? Types of reactions, first type, that is combustion reaction. Combustion, last year you learned burning. Combustion means burning. Combustion, for us it is hydrocarbon burning or any compound burning. For example, a hydrocarbon C4H10 butane, C4H10 on burning in presence of oxygen, any hydrocarbon on burning in presence of oxygen will be getting carbon dioxide and water. So I'm writing carbon dioxide and water. The amount of energy accompanied when 1 mole of that hydrocarbon is burnt. How much amount of energy on burning energy is released? How much amount of energy is released? How much amount of energy is released when 1 mole of that is burnt? So this is 1 mole. When 1 mole of this hydrocarbon is burned, how much energy is released? Released amount of energy is always negative. So here, delta C stands for combustion. At standard condition, there will be a minus sign for combustion. There will be a minus sign because energy is released. Okay. How much energy is released when 1 mole of this hydrocarbon is burnt? That is called enthalpy of combustion. Enthalpy of combustion. Now, C4, there are only one, here you see carbon, so we are writing 4 here. H10, only H you are seeing only there, so it will be H10, then it will be 5H2O. Why? Because we have taken 1 mole here, this 1 mole. 1 mole here, so there will be 10H, so 5H2O. Then you come to balance this oxygen. So there it is correct, 4 carbon dioxide correct, 5H2O correct. So only those many oxygens are utilized here. So here how many? 4 into 2, 8 oxygen, and here 5 oxygen. So 8 plus 5, 13 oxygen. Here you have to write O2 only. So here it will be 13 by 2 O2. This is the balancing of such equations. So the amount of energy released, how much amount of energy released? 2658 kilojoules per mole. So 2658 kilojoules per mole. This much amount of energy is released per mole. Per mole, this much amount of energy is released. This is what butane. This butane is used in daily in our kitchen in the gas cylinder. We are burning daily butane. So butane, how much amount of heat? A very high amount of energy is obtained. Using that heat energy, we are cooking our food. So this is enthalpy of combustion. When 1 mole of this hydrocarbon, 1 mole of a substance is burnt. Write down. Standard enthalpy of combustion is defined as. Standard enthalpy of combustion is defined as. Standard enthalpy of combustion is defined as the enthalpy change the enthalpy change when one mole of a substance, in standard states, is completely burnt, to form products under standard state. Standard state means this is gaseous state, this is liquid state, this is gaseous state, this is gaseous state. And standard states. Products under standard states. Next, enthalpy of atomization. Enthalpy of atomization means atoms are formed from what? From the molecule. Enthalpy of atomization. If you take one piece of metallic sodium and give energy to break this, to shift this, to move these sodium atoms from solid state to gaseous state, we call it as sublimation. So here enthalpy of atomization is sublimation. Enthalpy of sublimation, sodium atom, all in gaseous state. From the solid you can buy, in the form of solid only, from the market you can buy sodium, one piece of metallic sodium, looks like our paneer only. So when you take metallic sodium in the solid state and give heat energy, so that it is getting converted into atoms. So many atoms in the gaseous state. Means we have atomized the sodium. From the solid we have converted them into gaseous state, means single atoms are there in the gaseous state. How much amount of energy is utilized to atomize? Means atoms in the solid. Atomize, that is called enthalpy of atomization. This atoms can be made by breaking the bond also. For example, H2. From H2, how can you make H atoms? H bond H. You are making it as H and H. I'll be writing 2H gaseous state. So how much amount of energy is required? That is called enthalpy of atomization. You know that for 30 kilojoules of energy is required for this conversion. If it is metallic sodium, that is sodium in the solid state, changing to sodium atoms, sodium in the gaseous state, how much amount of energy is required? That is called enthalpy of atomization. Here from solid to gas means it is sublimation, that is 108 kilojoules per mole, 108 kilojoules per delta H. So here we are writing it as delta AH, means atomization. It is again sublimation, this much kilojoules per mole. Here delta AH, that is 430 kilojoules per mole. Or if it is given 435, then it is 435. So in some numericals they give 435, some numericals they give 430. So for 435 means 435 kilojoules per mole. So here atoms are formed. See here also atoms are formed. That is enthalpy of atomization. Write down. It is the enthalpy change. It is the enthalpy change for breaking of 1 mole of bones. You cannot take 1 bone, 1 mole of bone, 1 mole of bones. One mole of bones completely to obtain atoms in the gaseous phase. Atoms in the gaseous phase. It is also called bond dissociation enthalpy, BDE, bond dissociation. To dissociate this bond dissociation enthalpy, bond dissociation, the bond between them, bond between 2 atoms are broken and atoms are now free. Now, enthalpy of atomization, for the same bond there may be different enthalpy of atomization due to the difference in their environment. For example, CH4. CH4. If I take 1 mole of CH4, there will be 4 moles of bonds. because one molecule has got 4 bonds. If I take 1 mole of CH4, there will be 4 moles of bond. So to break all this bond into carbon, solid and hydrogen gaseous state in their standard states, how much amount of energy is required total? When 1 mole of bond is broken, when one mole of CH4 that contains 4 moles, this is for 4 moles. When 4 moles of bonds are broken, here 1665 kilojoules of energy is required to break this. This is for 4 moles of bonds. This is for 4 moles of bonds. This is in the gaseous state. This is for 4 moles of bond. So what is the average bond dissociation enthalpy for 1 mole of bond? That is divided by 4. So here 416 kilojoules per mole. So that is for 4 moles of bond. Now for 1 mole of bond, there is 416. That is the average. But for breaking this, different amounts may be required. Let's say average is 416, but individually, what is that? Individually, from CH4 gas to CH3 gas and H gas, bond dissociation enthalpy delta BDE, bond dissociation enthalpy, that is 420 at standard, that is 427 kilojoules per mole. 427 kilojoules per mole. This is the first bond. Only one bond we have considered. Now from CH3 gas to CH2 gas and H gas, delta VDE, bond dissociation enthalpy, H standard is equal to 439 kilojoules per mole. Again CH only, bond is CH only, but the environment is different. From CH2 gas to CH gas plus H gas, the delta BDEH is equal to 452 kilojoules per mole. 452 kilojoules per mole. And the last one, CH gas to C gas and H gas, that is delta BDEH standard is equal to 347 kilojoules per very unstable species, 347 kilojoules per mole. So according to the environment, when you add all these 4 things, you'll be getting 1665. When you add all those things, you'll be getting 1665. What is the average? Divided by 4. What is the average? Divided by 4. That is 416 kilojoules per mole. So to break the same bond, if the environment is different bond enthalpies are required. To break a single bond, to break a double bond, you have to supply more amount of energy to break a double bond. If it is a triple bond, again triple attraction, you have to supply again more amount of energy to break a triple bond. For example, O double bond O. O double bond O, 498. H single bond H. H single bond H, 435 kilojoules per mole. O double bond O, 498 kilojoules per mole. N triple bond N, 946 kilojoules per mole. So more bonds means more attraction. To break them or to atomize them, you have to supply more and more amount of energy as the number of bonds between them increases. Next, enthalpy of reaction. Next is enthalpy. Enthalpy of a reaction. During a reaction, some bonds are broken and some bonds are formed. Bonds between the reactants are broken and bonds between the products. Bonds between the products. Bond between the product atoms. Bonds between the reactant molecules broken and bonds between the products molecules formed. During the formation, energy is released. To break a bond, energy is required. To break a bond, energy is required. During the formation of a bond, energy is released. Now, enthalpy of reaction. What is meant by enthalpy of reaction? Right on. In terms of bond enthalpies, enthalpy of reaction in terms of formation, we have already written that is products sigma products minus sigma enthalpy of products minus sigma enthalpy of reactants. But in terms of bond enthalpies, it is just ulta. That is sigma bond enthalpies of reactants minus sigma bond enthalpies of products. Same thing, that is enthalpy of reaction. Previously also we learned enthalpy of reaction. Again, this is in terms of bond enthalpies. So enthalpy of reaction, enthalpy of reaction is equal to sigma bond enthalpy of reactants minus sigma bond enthalpies of products. Enthalpy for reaction in terms of enthalpy of formation we have written, that is, and that time products minus reactants. Here it is reactants minus product, same thing, enthalpy of reaction. It was formation value, enthalpies of each substance. Here in terms of bond enthalpies, means to break the bond, how much? To break the bond. Bond enthalpy of a bond enthalpy means to break the bond, how much amount of energy is required. So write one question. This is an approximate method. So you'll write one question. Calculate the bond enthalpy of HCl. Calculate the bond enthalpy of HCl means to break the bond between H and Cl, how much amount of energy is required? That is what is meant by bond enthalpy of HCl. Given that bond enthalpies of H2 and Cl2 are, given that bond enthalpies of H2 and Cl2 are 430 kilojoules per mole and 242 kilojoules per mole. 242 kilojoules per mole respectively. 430 kilojoules per mole and 242 kilojoules per mole. And delta FH standard. Delta FH standard. Delta FH standard means this is the formation value. What we learned previously in previous classes. Delta FH standard for HCl is minus 91 kilojoules per mole. What is meant by delta FH standard for HCl? That means 1 mole of HCl is formed from its constituent elements. 1 mole of HCl is formed from its constituent elements in the most stable state. Constant elements that is H2 plus Cl2, H2 gas in their most stable state. When 1 mole is formed from their constituent elements. So 1 mole is formed. To get this 1 mole, it should be half H2 and half Cl2, right? Half H2 and half Cl2, which is equal to, that is delta FH standard is equal to minus 91 kilojoules per mole. This is what is meant by enthalpy of formation. Enthalpy of formation. Now, question is find out the bond enthalpy of HCl. Bond enthalpy of HCl, and we know that just now we have learned that is this is a reaction. Of course, this is a reaction. This is a formation reaction. So, in terms of bond enthalpy, how can we write bond enthalpies of reactants minus bond enthalpy of product? Question is, what is the bond enthalpy of this? So, I am going to write bond enthalpies. Bond enthalpy of a reaction, that is minus 91 is equal to bond enthalpies of reactants, that is half into 430. Half into 430 plus half into Cl2. Cl2 value is what? 241, 242. That is 242 minus bond enthalpy of that HCl minus HCl. So enthalpy of reactants minus enthalpy of products is equal to enthalpy of reaction. Enthalpy of, this is enthalpy of reactants minus products. Reactants minus products is equal to enthalpy of the reaction. Enthalpy of reaction, here it is formation reaction, 91 is given. This is 91. So we can calculate, that is 430. That means 215 plus 121 minus, okay, plus 91 is equal to bond enthalpy. So you can calculate it as 427. 427 kilojoules per mole is the bond enthalpy of HCl. Bond enthalpy of HCl. So this equation we have written from the previous topics. That formation, when you know the standard enthalpy of formation you have learned, that is when 1 mole of a substance is made from its constituent elements in their most stable state. Okay, that's about enthalpy of reaction. Next type of reaction is enthalpy of solution. Enthalpy of solution, write down enthalpy of solution. Enthalpy of solution, it is, okay, it is the enthalpy change. It is the enthalpy change when 1 mole of it, when 1 mole of it dissolves, means 1 mole of the substance is getting dissolved. When 1 mole of it dissolves in a specified amount of solvent. In a specified amount of solvent. In a specified amount of solvent. So when you put some salt or some substances water, if it is soluble, sometimes heat is absorbed the solution. If you touch that solution, you may feel cold. Sometimes if you touch that solution, you may feel warm. So if it is warm, means during this dissolution, heat energy is released. If it is cold, that means during this dissolution, heat energy is absorbed. So you know that when sodium chloride, common salt, is dissolved in water, the solution will be having a lower temperature. But if you dissolve some detergent powder, soap powder in water that is warm, the solution becomes warm. So there is heat, sometimes heat is released, sometimes heat is absorbed. How much amount of heat is released or how much amount of heat is absorbed, that is called enthalpy of solution. That is when 1 mole of it dissolves. When 1 mole dissolves in a specified amount of solvent. If the solvent is infinite amount, then we call it as enthalpy at infinite dilution. Enthalpy of solution at infinite dilution. If infinite amount of solvent is there, we say enthalpy of solution at infinite. Enthalpy of solution at infinite dilution. Okay, let's consider one example, that is sodium chloride dissolved in water. When sodium chloride is dissolved in water, NaCl solid, when it is dissolved in water, Na plus aqueous and Cl minus aqueous. How much heat energy is accompanied during this reaction? That is called enthalpy of solution. So I am writing it as delta solution at standard. Delta solution at standard. Now, actually this can be taken through 2 steps. How can we find out the enthalpy of solution? Enthalpy of solution experimentally you can find out. Now the same reaction, consider that has a slow, I am taking through 2 steps. That is here Na plus gaseous state and Cl minus gaseous state, and in water, that is hydration enthalpy. So here I am writing hydration enthalpy. And here I am writing lattice enthalpy. See, 1 mole of solid is getting converted into the gaseous state. That is delta lattice H standard. So the same single step I am taking through 2 steps. So that is equal to this plus this. Hydration enthalpy you can measure experimentally. Delta H solution also you can measure experimentally, but delta lattice experimentally you cannot find out. So from the solution, using the solution and hydration, you can find out this delta H lattice. And here this enthalpy of solution is equal to delta H lattice plus delta H hydration. So here I'm giving you the value of delta H hydration, that is minus 784. Minus 784. So enthalpy of solution, suppose you want to find out enthalpy of solution. Enthalpy of solution, for that we are going to use the Hess's law, that is enthalpy of lattice and enthalpy of hydration. Enthalpy of hydration can be determined by enthalpy of hydration can be determined experimentally, but enthalpy of lattice cannot be determined experimentally. So we are going to find out the enthalpy of lattice, means lattice enthalpy through another method called Born-Haber cycle. So for this much portion we are going to some other topic that is called Born-Haber cycle. After that we will be coming back to this portion, and after finding out this you will be adding this plus this to get enthalpy of solution. How to find out the lattice enthalpy by Born-Haber cycle? Born-Haber cycle. What is Born-Haber cycle? Write down. Enthalpy diagram showing the sequence of different steps. The sequence of different steps of a reaction is called Born-Haber cycle. Born-Haber cycle. Born-Haber cycle. Full stop. Sum of enthalpy change around the cycle is 0. Sum of enthalpy change around the cycle is 0. Around the cycle is 0. So I am going to find out lattice enthalpy by Born-Haber cycle. For that, see, finally, ultimately, sodium chloride lattice enthalpy. We have to find out. What we can buy from the market is Na solid and Cl2 gas. And here 1 mole of NaCl is to be formed in the solid state. This is the ultimate reaction. So here okay, we'll continue in the next class. Time is over. Thank you.